Okay, I'm just going to adjust the camera. Perhaps the easiest way to do that is turn this. There, that should make us a little less seasick. Okay, so this is a little awkward teaching to an empty class, but it's nice to see some faces here. Every once in a while, I'm going to have to go down and check to see if there are any questions and things that are going on. But our goal for today was to prove some of our laws of logarithms that we had taken a look at and kind of talked our way through yesterday. Once we prove a few of these laws, and I'm only going to prove two of them, I'll leave one other law for you to prove as a part of your homework assignment, and then we'll take a look at solving some exponential functions. Can I get a volume check? Is the volume working out okay on this? Just give me like a couple of plus signs if the volume is working good. Okay, it looks like the volume is working fine. Perfect. So, just before we get into proving one of our laws of logarithms, let's discuss what a direct proof is with a concept that we likely proved in grade 9. So this is one of our exponent laws. And I mean, we talked about this when we were introducing our laws of logarithms as well. And this law simply states that if you multiply powers with the same base, then you add the exponents. But how do we know this is true? Well, I mean, we can know it's true by substituting in numbers and doing test cases, but that only works for specific values. What we really want to do is we want to try and make sure that we can have this work for all values in general. So we're going to stick with these general terms, but we're going to start with the left side and then navigate a mathematical argument to get to the right side. So for instance, let's start with the more complicated left side here. What we have is a to the power m times a to the power n. Now, what does a to the power m actually mean? This would be kind of funny if you wanted to type it out in your comments on your keyboard right now. How would I write a to the power m? This also gives me a coffee break. See, it's just like real class. Snow days. Okay, I'm not seeing any comments with the potential answer. So a to the power n would just be a group of exactly m a terms. Thank you very much, Adam. And so then what would I realized I maybe just went a little bit too fast for you to type it out or to realize how to type it out. But I think that's exactly what I see in my comment. So then what will I see right next to this? So this is the first expression of a to the m. And I should expect to see what for the second expression for a to the n, but the same thing. but instead of having m of them, I'll have n a terms. Can you see the board all right? Is the board reverse imaged? Sorry, welcome, come on in, it's okay, join up.
Okay.
We've just started, don't worry.
Okay. Can we watch this after too?
Yeah, you can watch it afterwards as well.
Okay.
Sorry, we just had someone walk into class. Okay, I looked at my screen and I thought that it was reversed image, so just making sure it's good. But essentially we've got m a terms and n a terms, and so we have a multiplied by itself m times and a multiplied by itself n times. So if we just go ahead and count up all of the a's, well, I count up to m and then I count up m plus 1, m plus 2, m plus 3, m plus 4, m plus so on until I have counted all of the n a terms. And so what I end up with is a to the m plus n. So this is a little bit more rigorous of an argument than just saying, believe this because I told you it's true. So we're going to go ahead and do this proof for our first law of logarithms, which is going to be our addition law for logarithms. So what we need to prove is that statement. We need to prove that logarithm base A of a product is equal to the sum of the logarithms.
Don't we have math next period?
Yeah, I'm sorry for the interruption. Yes, I know we have math next period, but it's a live stream, so you'll be able to go online and like look at it and pause the video and that sort of thing. I just need to make sure that I can cover all of my live streams before the weather gets too bad. So I'm doing one for you guys and then one for the other Math SL group as well too.
Well, live stream on, sorry to interrupt.
Okay, no worries.
So are you going right now then? No, it'll be online. So.
Just bear with me, folks. There's only like 4, well, I think that's Hallie too. Someone else is watching just for the sake of watching a live stream of math. So good job for you, by the way. If you want to come in, you can.
Okay, did you just start?
I started at 9:45.
Okay, well, okay, I'll just write this down. Okay, I'm
Okay.
in chemistry.
Okay,
I'll
see you
be
later.
back.
Sorry about the interruptions, folks. And anything you say is probably being recorded as well, so they can probably hear you too. It's okay, you can like ask questions and answer things. Sorry about the interruption. So we need to prove this property of logarithms. So we have to start off with either the left side or the right side. And I suppose we'll put it to a vote right now. So would you like me to start off with the left side or with the right side? It's entirely your choice. This could be a little bit painful, by the way, too, because I'm going to actually ask you guys for each of the steps as we go through this. I'm not just going to give you the proof. I'll let you kind of play around with it for a few minutes, and then I'll start guiding you toward the right answer. So any votes for left side in the comments? Ah, perfect. We got to vote for left. So Adam spoke up first, so we'll start with the left side. So my left side is the logarithm of A, B, C. Now, unfortunately, we can't use a fact that we need to prove in the proof itself. I mean, logically, that doesn't make sense. It would just be a circular argument. So we have to come up with something, some way to break this up in another method. I'm going to give you a hint, and the hint is, I don't know how far over I can go. I'll go back over here for the hint. The hint is, remember that if we have an exponential expression like this, then this is equivalent to the logarithmic expression of that. So that's one hint. And I'll give you another hint as well, too. And so that is, if we have the logarithm of base A to the value A to the power n, and this just means it's equal to n. Because what exponent do you need to raise a to get to a value of a to the power n? Well, obviously n. So we may need to make a change of variable somewhere. Leave you a minute to think about the hints and perhaps suggest something. Anything? Okay, now normally in class, I would let you suffer through this like long pause of silence until somebody broke the silence and started to speak. But I think what I'll do, just so that it's easier to maybe go back and watch this video again, is I'll guide you toward my suggestions. So suppose we wanted to be able to change B and C so that, like in our hint, they were written as a power of A. And in fact, I can do that. I can say that A to some power is equal to B. Because I know that if A and B are integers, if they're positive, then I can find some power that raises one number to another. If I needed to raise 2 to 7, I can find that power using logarithms. If I needed to raise 2 to 8, I could find that power just by knowing that 2 to the power 3 is 8. So I can make that substitution. I can also make this substitution, that A to some other number n is equal to C. Now, in making that substitution, my left side becomes logarithm of a to the m times a to the n. So we've gone from here, we've created a substitution, and we're now here. Now, what's a to the m times a to the n? It's okay, say it.
M plus n?
Yeah, we can change this to the logarithm of a, base a, to the m plus n. And that tells me something about what this simplifies to, and this should be easy to type into the comments. So what will my very next line be? Take a look at the hint if you need it. I wish that they could voice talk back because it's just so awkward, like trying to look into a screen. And then this being broadcast out to them is awkward. And then me referring to them as them is also
You
awkward.
need like a
It's
Skype,
there needs to be like a, what do they do? Like a group face chat or whatever. Like that's the thing that it needs to, like, this is good. The nice part is it's recorded, so you can go back and look. Adam, that's not a bad guess. So where we have this expression, our exponent just comes down. These don't end up multiplied though. These do end up added. So you're just missing one sign there. This will end up being not the product of m and n, but the sum of m plus n. So when we have a logarithmic expression like this, the power required to raise my base a to the value a to the power m plus n is just m plus n. It's like saying, what power do I need to raise 2 to get it to 2 to the power 3? Well, I need to raise it to 3. So the 2's just cancel out, or in our case, the a's just cancel out, and we're left with m plus n.
Should be log.
No, the logs cancel out too, because remember, this is saying, what's the exponent required to raise a to the exponent m plus n?
Okay.
It's easier to explain in the hint. So what's the exponent required to raise a to a to the power n? Well, it's just n. That's the exponent you need. Now, at this point, I'm going to have to erase my board. So we're going to assume that this line is just going to carry up. I just don't want to have to turn the camera and fumble through that and make it more awkward. So I am going to erase this part of the board. Although I am going to leave my substitution up. I believe you can just go back in the video, like you can zoom back to see what's going on, or pan back, or I guess go on the timeline back. But we'll carry this m plus n up to the top. And now I seem to be in a worse off place than I was at the beginning. Because at least at the beginning, I had logarithms. And I had a's, b's, and c's. Now I don't. But what I do have, which is nice, is instead of having one term, I've got two terms. And two terms is a lot closer to what I want to prove. I needed to create two terms, and I've done it. The hint comes in the fact that these two statements are in exponential form. What other equivalent form could I use? So I could use hint number 2. I could change from exponential form to logarithmic form. Now, if I change this to logarithmic form, what will it become?
Log of base A to B M.
And that's equal to
M.
Yeah. And so that's converting the first statement into logarithmic form. Go ahead and convert the second statement into logarithmic form. And I'll let the people at the computers do it first for a second, and then I think our in-studio audience has a solution for us as well too. And so what will this become?
Log of A to C equals N.
Great. So now that we've converted back to logarithmic form, and yes as well, so thank you for the comment as well, Adam. That's correct too. Now we can back substitute because we had m plus n, and we know m is equal to log base A value B. And we know n is equal to log base A value C. And actually, isn't that exactly what we set out to prove? It is. We started off with the left-hand side, and through a change of variable, or a change of base, no, sorry, change of variable, not change of base, and then changing back after we used one of our exponent properties, we've proven, starting from log A, B, C, that it ends up being able to be broken up into the two separate logarithms of log AB and log AC. So that proof is essentially the same as the proof for when you have a logarithm of a value that's divided, so breaking something up by division. Now, I'll just remind you of what that one is. If I erase right now, is it okay? Like if I erase right now, will you be able to go back, the computer folks, when this is over, will you be able to go back and see what was on the board? I guess you can always take screenshots too. Cool. I'm just going to go ahead and erase. So if you follow the steps to that proof, then you should also be able to prove this one. And they'll be very similar. You'll do that same substitution. You'll do that same manipulation based off of our exponent laws. You start with the same thing as well that Adam had suggested, the left side. and then you move your way through, you substitute back from logarithmic form, and you should be able to reach a similar style proof. So that's that log property. Now we're going to prove, I believe we did prove, no, we didn't prove the product one. Let's prove the product one. So we're going to skip this. I'll leave this as homework. So do as homework. And I'll leave my same hints up because we're going to be doing a similar sort of thing. But our next proof that we're going to do is this one. And I'm going to suggest that we start from the left-hand side and keep that same idea of creating another variable or expressing one variable in terms of another, and then seeing how our exponent laws work out for that. So we'll start with the left-hand side, which is log a b to the power c. And then at this point, it would be really nice if we could use hint 1 somehow. So how will I do that?
Oh, you just write it as C?
We can't just write it as C, but if I wanted to write it as C, I would need B to be written as some term of A. So similar to our last proof where we just said, okay, I can write any number as some other number to some other power, I have to create that statement. So I have to say that B is equal to A to some power. So we just create up a letter. So pick one, any letter. Hit the first letter you want on the keyboard. Don't use E, I, or A, or B, or C. Nobody's voting. This is where in the comments I explained that it was probably going to be dicey because the interaction's tough back and forth. Thank you for your patience. We'll just use M, I suppose. And so now I can back substitute in. And I have B to the power C. Oh, sorry, Adam, you're just a little bit late on K, but I like that choice. This is kind of written a little bit too close to C. Just move this off to the side. B equals, yeah. So now what exponent law will I use to simplify the value of my logarithm right now? So I can ignore the logarithm in the base part. I just want to simplify this expression. What will it become? This will become log A to the MC. And as Ali said in class, this simplifies in much the same way that the previous one had. Our log A's will in fact cancel out. We'll just be left with M times C. And very similar to our prior proof, that expression we created to substitute in for B in exponential form can be converted to logarithmic form. When we do that, what will it become?
Is it log A to the V, then to the exponent X?
It just equals M.
Yep.
So we're just converting back into logarithmic form, and now we have something we can substitute. So we know that m is equal to log AB. Now, MC and CM is the same. Multiplication is commutative, so I can move around. So I'm going to write this as C times my value of m, which is log A, value B. Which is exactly what I had set out to prove. Fantastic. And those are two proofs of our properties of logarithms. Again, I'll leave the change of base 1 up to you, and I'll also leave when we have values that are divided up to you. Now we'll just do a few examples of using these to perhaps combine some logarithms together and solve some things. So this is it for the proof section. I'll just do one or two examples. I think rather than kind of pausing and asking questions, I'll still ask the question, then I'll look awkwardly into the camera in the audience, and then I'll provide the solution so that we can move this along, because I have another stream starting up at 10:30. So let's do a couple of examples with these. Let's go with 2. Sure. This may not work out nicely, and in fact, I'm kind of hoping that it doesn't. So we're going to try to solve an equation that looks like this. Logarithm of x plus the logarithm of x plus 1 equals 2. Now you can certainly solve this on your calculator. You can set y1 equal to this expression and y2 equal to that expression. Look for where it intersects. There may be more than one intersection point. And that would be a method that you could use your calculators to solve. But whenever I see multiple logarithms, I usually look to combine them or condense them into one logarithm. So because these have the same base and I'm adding them, well, what can I do to their values instead? That's the awkward pause. I can multiply them. So this is, remember, a common logarithm, so it has a base 10. So this is using that property that we have of log ABC equals log AB plus log AC. Except I'm going to be using it backwards. So this will tell me that this side becomes log x times x plus 1 equals 2. And with most logarithmic equations, the key is combining till you have a single logarithm and then going ahead and simplifying or converting into exponential form to solve. So at this point, I'm in logarithmic form. My base is 10. I can go ahead and convert this into exponential form. So the base is 10, the exponent is 2, so this becomes 10 to the power 2. And the value is left, so this ends up being x squared plus x. Now I have a simple quadratic to solve. Now 10 to the power 2 is 100. So I've got this quadratic. And we know that this quadratic opens up and has a y-intercept of negative 100. So it is going to have two real roots because it starts below the x-axis and it comes up and through. I'm trying to think of numbers that factor for this. So what times what is 100? Well, we've got 10 times 10, 25 times 4. 5 times 20. I don't think I'm going to get close to factoring, so I'm probably going to have to use the quadratic formula. So I'll use the quadratic formula real quick. So this is going to be negative b plus or minus the square root of b squared minus 4ac. So that's going to be plus 400. all over 2a. It's 2. So this gives me a couple of values. X equals -1 plus or minus root 401 over 2. And these are potentially my solutions. Now, the reason why I say potentially is because remember when we were first studying logarithms, we found that you couldn't use a negative number in the value. So our x portion couldn't turn out to leave a negative value in the original equation. Here, there's no exponent that I can raise 10 to make it negative. Even if I use a large negative exponent, it'll still just bring it really close to 0. I can never get it to be a negative number. So one of these solutions is a negative number. The square root of 401 is really close to 20. It's around 20 and a couple of decimal points, right? So this is -1 plus 20 divided by 2, which would be around 19 divided by 2, so around 9.75, something like that. So with the positive sign, this ends up being an actual solution, because if I put around 19 into there, there's an exponent I can raise 10 to get to 19. And if I put around 20 into there, there's an exponent I can raise 10 to get into around 20. But when I go through with the negative portion of the quadratic formula, it's going to create a number like -21 over 2 or -10.5. Well, there's no power that I can raise 10 to get to -10.5. This is what we refer to as an extraneous root. So the solution is x equals -1 plus root 401 over 2, and x equals -1 minus root 401 over 2 is extraneous. It's extraneous. It was created when we did our algebraic step of combining our logarithms, because this technically changed the domain. Here the domain is everything where x is greater than 0. Here the domain is everything where x is greater than -1. But here, our argument ends up being a quadratic, x squared plus x, which is positive in a region ahead. It's also positive in a region behind, just because of the nature of parabolas. So here's one example of using our properties of logs. There's tons of examples in your textbook that you can work through. I think it's safe to work through chapter 2, with exception to graphing logarithms. Obviously tomorrow, hopefully we'll be in class, and sorry, I see someone shaking their head, which means it's part of the in-studio crowd. Yes, I'm saying it's a crowd. You guys can't see it, so I suppose you can't tell whether I'm telling the truth or not. But tomorrow, hopefully we are in class, so that way we can go over more examples of this. If we have to do another lecture tomorrow, we will. It'll be on graphing logarithms, and then we'll take the remainder of the week to kind of clean up our work with logarithms and move forward to sequence and series. So that's all for today. Thank you for tuning in, and don't forget to like the video, subscribe to my YouTube channel, and all the other things that people say about stuff like that. Obviously, I'm kidding. You don't have to like it. If it ever deletes off of here, feel free to ask me to go and repost. I don't know how to do that, so feel free to come show me how to do that. And please send me some feedback about whether this worked or didn't work. Whether you do that in the comments here or whether you send me an email, that's okay. So have a great day and stay safe. If you're going outside, wear a tube.